We are delighted to announce that Silvana Martini will receive a 2021 AOCS Fellow Award. Dr. Martini is a professor in the Department of Nutrition, Dietetics, and Food Sciences at Utah State University. Her research focuses on the physiochemical and sensorial characterization of food materials, particularly lipids. She studies how the quality of food materials is affected by their nano, micro, and macroscopic structure. Dr. Martini pioneered the use of ultrasound to change the physical properties of fats. This research has tremendous potential for the fats and oils industry. Dr. Martini has published more than 110 papers in peer-reviewed journals and 11 book chapters. Her work has been recognized by awards including the AOCS Timothy L. Mounts Award in 2019 and the American Chemical Society's Young Scientist Award, Agricultural and Food Chemistry Division in 2014. Dr. Martini is also the director of the Aggie Chocolate Factory at Utah State, which opened under her supervision in 2018, not only to sell chocolates, but also to educate students in the school's food science program. Dr. Martini has been part of the AOCS community since 1999. She has chaired groundbreaking sessions at annual meetings and the Latin American conferences, led the Recognition Program Committee, and since 2019 has served as a member of the AOCS Governing Board. Most recently, she was selected as the editor-in-chief for the Journal of the American Oil Chemists Society after making significant impact as a senior associate editor for the same journal. Silvana Martini is a highly skilled leader and exceptional teacher. Thank you, Dr. Martini, for your outstanding contributions to the scientific community and meaningful service to AOCS. Congratulations, Dr. Martini.
Welcome, everybody. Thank you for joining us at the 2021 AOCS Fellow Award Lecture. As you can see, Sonocrystallization of Fats. My name is Rich Hartel. I'm a professor at UW-Madison. I'm delighted to introduce Silvana Martini, a new 2021 AOCS Fellow. As you know, these Fellow Awards recognize achievements in science and extraordinary service to the society. A little bit about Silvana. She's a professor in the Department of Nutrition, Dietetics, and Food Sciences at Utah State University. Her research is on physicochemical and sensorial characters of food materials, particularly in lipids, and how the quality of food materials is affected by their nano, micro, and macroscopic structure. Silvana has published more than 100 papers and book chapters, and her work has been recognized with numerous awards, including the AOCS Timothy Mounts Award in 2019. She's been a part of the AOCS community since 1999 and has several leadership roles, including the Professional Educators CIG. She serves as Senior Associate Editor for JLCS, but that will change pretty soon. She'll become the Editor-in-Chief, and she's also a member of the AOCS Governing Board. And with that, Silvana, thank you for everybody for joining us, and I'll turn it over to you for your presentation.
Great, thank you, Rich, for the great introduction. I also want to thank AOCS for the award. It's really an honor to be named an AOCS Fellow. I want to thank Dr. Mogis Ahmad for the nomination, and also all the people that wrote the support letters, of course. Back in 1999, when I attended my first AOCS meeting, invited by Dr. Maria Lidia Herrera from Buenos Aires, University of Buenos Aires, I never thought that more than 20 years later, I would be giving a presentation for an AOCS Fellow Award. So it's really an honor for me to be here, and thank you very much. I really appreciate that. So today I would like to talk about some of the research that we've been doing in our lab for over 15 years now on sonocrystallization of fats. So for those that know us, we've been working with ultrasound for a few years since I've been here in Utah State. And today I'd like to focus more on what are the things that we need to know about ultrasound if we want to use this technology for industrial applications. Say that you're working with a fat and you are considering novel technologies to improve the physical properties of the fats, and you heard about ultrasound. So what are the things that we need to know to make this happen and to really evaluate whether ultrasound will be a solution or not? So let's start with what is sonocrystallization. So sonocrystallization is the use of acoustic waves to induce the crystallization of materials. And sonocrystallization is not new. By far, it has been used for a long time to induce the crystallization of especially drugs, and to induce basically what ultrasound is used to generate a very pure material and induce the crystallization of these materials. So if we talk about acoustic waves, we know that acoustic waves are waves that operate over a wide range of frequencies. And frequencies can go from below 20 hertz, and those are the frequencies that are detected by elephants and whales and crocodiles. And then we can increase the frequency between 20 hertz to about 20 kilohertz, and those are the frequencies that humans can detect. And then we can, if we increase those frequencies a little bit higher, we go into the ultrasound region, and that's usually acoustic waves that, for example, bats can detect. So based on those, on that frequency range, we can characterize, or we can divide acoustic waves into different categories as infrasound, audible range, or ultrasound. And within ultrasound, so when we talk about sonocrystallization, we are talking specifically about ultrasound. And within ultrasound, there are different techniques that you probably heard of. The one that we're going to deal with is high intensity ultrasound. And these techniques use very low frequency between 20 and 100 kilohertz. Second technique that I always like to introduce are low intensity ultrasound that uses frequencies between 100 kilohertz and 1 megahertz. And last but not least, diagnostic ultrasound that uses frequencies between 1 and 10 megahertz. So these two techniques, low intensity and diagnostic ultrasound, they operate at higher frequencies, and therefore they don't cause any changes, any physical or chemical changes in materials. So we are interested in this high intensity, high power ultrasound because we actually want to change especially some physical properties of our materials. So again, so high intensity ultrasound uses frequencies between 20 kilohertz and 100 kilohertz, and also very high power intensities between 10 and 10,000 watts per square centimeter, very high power technique. These acoustic waves are sinusoidal waves, and they are also longitudinal waves. What this means is that when a wave is propagated through the material, it causes movement of particles, and this movement of particle occurs parallel to the direction of the motion of the wave. So what does that mean? That means that if we have a wave, as again, we said it has a sinusoidal shape like that, is characterized by a wavelength, right? A frequency. And if the wave is propagating, for example, in this case, from left to right, the particles move in the same direction from left to right. So it is a very nice representation from Russell. And what I like from here is that you see that the particles, if you follow those red dots, the particles don't move from point A to point B. The particles really oscillates around their position, their equilibrium position, back and forth, back and forth. And what this does is creates zones in the material that have high density of particles and zones that have low density of particles. We call those rarefaction for the ones that have low density of particles, or compression zones for the ones that have high density of particles. And those low and high density of particles are correlate with the peaks of the acoustic wave. Now, the thing here is that when we apply ultrasound, if the power is high enough, the difference between the compression and the refraction is very big, and that is going to create tension in the material. And that tension is going to create a void, and that void is going to grow with enough power and is going to create a cavity. And that cavity is going to grow even further and form a bubble. And this is important because it creates a phenomenon called cavitation. And all the studies that have been done on ultrasound or high intensity ultrasound explain the results that are found based on cavitation events. So really the formation of these cavities or bubbles and the dynamics of these bubbles are the ones that are creating changes in the physical or chemical properties of the material. So again, cavitation, so say that we have an ultrasound tip, this is what it would look like, and all those bubbles are being generated. While we apply ultrasound, those bubbles grow, and at some point, the walls of the bubbles are going to become very stressed and very unstable, and the bubbles are going to collapse. And this collapse is going to be associated, it's going to happen very abruptly, it's going to be a high energy phenomenon. And this bubble collapse is going to create high shear rates, is going to create high temperatures, high pressures. And again, these high temperatures, high pressures, high shear rates are the ones that are going to be responsible for changes in the physical and chemical properties of the material. So if we look at what sonication looks like, this is a video that we took in the lab. We can just forget about this is the hydrophone. We were doing this as part of another experiment. This is the tip that we use to apply ultrasound. The material here is vegetable oil, so we don't see any crystals. And you can see that there is a lot of movement here. You can see the bubbles, you can see what we call a cluster. And you can really see the shear and the really aggressive conditions that the material is subjected to. We repeated this experiment with a high-speed camera. This is a collaboration that we have with Dr. Peter Birking and Tad Truscott, that they're helping us understand the mechanisms of cavitation that occur in the oil. Cavitation has been studied a lot in aqueous systems, but not as much in oil systems or lipids. So we are doing quite a bit of progress. I'm not going to talk too much about this today, but if you're interested, let me know, because over the last 3 to 4 years, we made a lot of progress on this area. So, but just to show you how, so this tip is the same tip as we showed before, right? So it's a 3.2 millimeter diameter tip, and we see a cluster of bubbles that are generated very close to the tip. We can see the tip oscillating back and forth, right? You can see that going up and going down. So the amplitude of vibration of this tip is what drives the power of the ultrasound. So when we say that we use higher power levels, that means that the amplitude of vibration of the tip is higher. And so we said that cluster that grows and collapses following a very specific periodicity. And we also see a lot of bubbles that we call the streamer of bubbles that travel very, very fast away from the tip. And we also see these really cute bubbles oscillating beside the tip. They're very stable. They oscillate, but they're very stable. They don't move much, and they oscillate based on the frequency and on the power level that we apply in the ultrasound. So based on these two figures, Dr. Birkin actually came with these really nice diagrams that I love to use to borrow from him, where we show the ultrasound tip, the cluster of bubbles, and the streamer of bubbles that flow or they travel away from that tip. So, ultrasound, as I said before, has been used to crystallize materials for a long time. But perhaps the first people that used ultrasound in fats were the group of Dr. Sato at University of Hiroshima. And they used ultrasound to change or to induce the formation of the most stable polymorphic form in cocoa butter and other triglycerols. So very good research showing the kinetics of crystallization of different polymorphic forms using ultrasound. Other groups that have used ultrasound in food systems are groups from the UK, where they used ultrasound to crystallize sugars and ice, and also a group that studied the crystallization of palm oil. However, up to the early 2000s or mid 2000s, nobody really used ultrasound or evaluated the effect that ultrasound has on the physical properties of fat. So that's where our group comes along, and where we started doing quite a bit of research evaluating how ultrasound can change the crystallization kinetics of fats and then the physical properties of the final material. So what we've learned so far, I'm going to show a few results here as a way of summary so that people can know the broad range of changes that we can induce by ultrasound. So the first one and the most reproducible and the most stable change that we find is on crystal size. So when we apply ultrasound, we see a significant reduction in the crystal size of the material. In this picture, I believe this is an interest-purified soybean oil. In the left, we have the sample that has been crystallized without ultrasound, so we can see the big crystals, white crystals in here. And on the right, we see a picture of the crystals obtained with the use of ultrasound. So a lot smaller, a lot more crystals. So very, very significant change obtained with ultrasound. The second change that we see is on hardness. So this is an example with milk fat. We crystallize milk fat at different temperatures. And of course, the black bars indicate the hardness of the non-sonicated samples, and we can see that the hardness decreases as we increase the temperature, which is something that we expected. Now, when we apply ultrasound, the hardness is significantly higher for all the temperatures that we tested. And to me, the interesting part here is that, for example, at 32 degrees Celsius, we can obtain the same sample, the same hardness that we would obtain at 26. So without ultrasound, right? So with ultrasound, we can generate the same amount of hardness, the same degree of hardness that we would have obtained at 26. So that means that I don't need to cool the sample all the way to 26 to obtain a hardness of, say, 3 newtons. I can crystallize at 32, apply ultrasound for 10 seconds, and I still get that high hardness. So that to me is a very significant result that could help save some money in terms of energy. As Dr. Sato proved many years ago, ultrasound can change the polymorphic behavior of fats. So we really corroborated this data by showing that ultrasound can induce the crystallization of the most stable polymorphic form. In this case, it was a high stearic, high oleic sunflower oil fraction. Also, one of the most important or more common effects of ultrasound is in the crystallization kinetics. So when we use ultrasound, crystallization occurs a lot faster. And really, I'm going to show some data later in this presentation that really, if we would let this sample crystallize or store over time, really the effect of ultrasound doesn't increase, for example, the solid fat content. It just reaches that final solid fat content faster. And again, I'm going to go a little bit more in detail about this in a little bit. And ultrasound, of course, also increases the viscoelastic properties of the material, especially the elasticity. This is an example of a sample crystallized with and without ultrasound on the values of G prime, significantly higher G prime values for this sample. In some cases, not always, but in some cases, ultrasound has an effect on the melting behavior of the sample. So say that you crystallize your sample and then you want to melt it. We sometimes see that the sonicated samples have a lower melting point. And this is an extreme case on a palm-based sample where we saw a significant decrease in the melting, in the peak temperature of the melting profile of the palm. And last but not least, recent research in our lab has shown that with ultrasound, we can decrease phase separation, oil migration, and increase oil binding capacity. So, you know, all these physical properties are important in fat systems, and especially important in fat systems with low levels of saturated fatty acids, where we might want to generate these physical properties that are lost due to a reduction in saturated fats. So perhaps I like to always show these pictures because this is perhaps the most drastic changes that we've seen over the different samples that we evaluated during these years. And this is a palm kernel-based confectionery fat that we crystallize at high temperature. So you can see these huge crystals, lots of liquids in here, a very flowy sample. So this sample was crystallized without ultrasound. When we applied ultrasound under exactly the same conditions, so the difference only is on the application of ultrasound, we get a fat that is a lot harder. It doesn't flow, and it keeps its structure when we grab it with a spoon. And this, of course, is related to the crystal sizes. We see those huge crystal sizes on the left and the small crystal sizes on the right. So very, very drastic effect of ultrasound on the texture of the sample in particular. So what is our hypothesis? Well, our hypothesis is that, first of all, as with any crystallization experiment, if you want to use ultrasound to crystallize your fat, the first thing that you need to do is to generate a driving force for crystallization. In the case of fat, that means that we have to supercool that fat. We have to cool the fat to a temperature below that melting point. And once that fat reaches that supercooling, we either can apply ultrasound in the absence of crystals or in the presence of a few crystals. And if we apply ultrasound in the absence of crystals, we're going to induce primary nucleation. And if we apply ultrasound in the presence of crystals, we're going to not only induce primary and secondary nucleation, but also those high shear forces and that huge movement that we generate when we apply ultrasound are going to break the crystals that are being formed and are going to help generate these smaller crystals that we see at the end of the crystallization process. So no matter how we apply ultrasound, really the effect is to change the crystallization kinetics of the material, to change the crystal size, and both these two things are going to affect the physical properties of the materials like viscoelasticity, texture, and melting behavior, and or binding capacity. So what are the challenges that we face when we use ultrasound? So the first thing is we need to identify the appropriate sonication conditions. So what part or where throughout the crystallization process I want to apply ultrasound? Is it better to apply it at the beginning of the crystallization process? It is better to apply it at the end, in the middle, what type of tip size we want to use, what sample volume, how long I want to apply ultrasound for. So all these things are going to affect the efficiency or whether ultrasound will work or not, or will be effective at changing physical properties. We also want to evaluate what is the effect of ultrasound in different fat systems. So one of the problems that we had is that, we started evaluating ultrasound in milk fat, and then when we changed to a palm-based sample, we had to start all over again. The conditions that work for one system doesn't always work for another system. So we kind of did a few research showing how ultrasound will work in fats with different levels of saturation of saturated fatty acids. And we also compared effects of ultrasound in palm-based versus soybean-based samples. So we're going to talk about that in a little bit. And we also need to know, or we need to realize that ultrasound is going to work differently whether we apply it on a batch system, on continuous, or whether we apply agitation or not. So we're going to discuss some of these topics today, and hopefully by the end of the day, we all will have a little bit more idea of what are the conditions that might work for a specific system and what are the conditions that might not work for a specific system. So the first thing that I'd like to discuss is how HIU, the effect of HIU is affected by crystallization temperature. This is one of the first works. This is actually the first paper that we published back in 2008, where we applied ultrasound to milk fat, AMF, and we crystallized the milk fat at different temperatures, 22 to 80 degrees Celsius. So as you can see, the amount of crystals change. As we increase the temperature, we have fewer crystals and bigger crystals. Now, when we applied ultrasound, the first thing is that we applied ultrasound in the absence of crystals. What does that mean? When we do these experiments, we melt the fat, we put the fat in a crystallization cell that is connected to a water bath so that we can control that crystallization temperature. And as soon as the sample is placed on that crystallization cell, it starts cooling down. And once the sample reaches that crystallization temperature, then we applied ultrasound. So when we applied ultrasound at 22 degrees Celsius, we see that actually ultrasound didn't work very well. We see here that there are a lot fewer crystals. There's a lot more black in this picture than in this picture, right? So it kind of melted the crystals a little bit. And that is because probably ultrasound was applied too close to the crystallization process. And we're going to talk about this a little in the next slide or two. But really ultrasound worked a lot better when the ultrasound was applied at intermediate temperatures between 24 and 28 degrees Celsius. We could see a significant increase in the number of crystals and a significant reduction on the size of the crystals. But however, when we applied ultrasound at 30 degrees Celsius, we didn't see any changes. We didn't see any effect of ultrasound in this sample. So we decided to explore this temperature a little bit further. And what we did is we lower the temperature, the power level a little bit, and we applied ultrasound at the onset of crystallization. So what if instead of applying ultrasound in the absence of crystals, we apply ultrasound where we see a slight turbidity in the sample? And that seemed to work, right? So if you see here, the first column is a sample that has been crystallized without ultrasound. And the second column is a sample that has been crystallized with a lower power level and at the onset when ultrasound is applied at the onset of crystallization. As we decrease the power and also decrease the sonication time, the duration of the pulse, we see also a greater effect of ultrasound in terms of crystal size. So really, if we wanted to apply ultrasound at a very high temperature, very close to that melting point, ultrasound will work better if it's applied maybe at lower power levels, shorter durations, and also at the onset of crystallization for sure. So this results in changes in crystal size where also seen as in terms of viscosity. So smaller generation of smaller crystals resulted in higher viscosity. As you can see here, the viscosity of the samples crystallized at 30 degrees Celsius with lower power level and shorter duration, significantly higher for the milk fat. And with of course we repeated this with another system like an interstratified soybean oil, and we also saw a significant increase in that G prime, in this case in the elasticity of the sample that was crystallized at the onset of crystallization versus the sample that was sonicated without the presence of crystal. So overall, really, over the years, we've learned that ultrasound works a lot better when it's applied at the onset of crystallization. So we continue doing our research, doing that, just applying ultrasound when we saw a slight turbidity in the system. So why do we think that's happening? Well, if we have a fat that crystallizes slowly, which would be the case of the milk fat that I showed before, crystallizing between, I would say, 24 to 28 degrees Celsius, or even 30 degrees Celsius. We have a fat that crystallizes slowly. We see the increase in solid fat content as a function of time. And say that we apply ultrasound at 10 minutes, that's when we still don't have any crystals in the system. But the system doesn't start to crystallize until, say, 40 minutes. And this will be the case of the sample that we crystallize at 30 degrees Celsius for the milk fat. So we apply ultrasound, we generate those bubbles, everything is fine. But by the time that the sample is ready to crystallize, the bubbles are gone, they dissolved. So the system is going to crystallize as if nothing happened. And we don't see an effect of ultrasound. And again, this would be the case of the milk fat at 30 degrees Celsius. Now, if we now apply ultrasound at the onset of crystallization, we generate those bubbles. And those bubbles are still going to be present, not only when the crystals are just being formed, but also during the growth of those crystals and the continuous nucleation of those crystals. And that is going to affect the crystal size and the crystallization kinetics. So now there is an interaction between those bubbles and the crystals that are being formed that are going to affect these processes. But what happens when we have a very fast crystallization, like in the case of milk fat crystallizing at 22 degrees Celsius? So if you have something that crystallizes super fast, we will see a solid fat content curve similar to this, more or less. And if we apply ultrasound in this condition, what is going to happen is that the crystallization occurs so fast that the bubbles are not going to be able to do anything about it because the crystals are growing like crazy, right? Even though we apply shear rate with the ultrasound, the kinetics is so fast that overrules the effect of ultrasound. And we see actually these with other processing conditions, like if we would test agitation or the effect of emulsifiers or additives into the crystallization of fats, we'll see that those effects become less important in a fat that crystallizes fast. So again, just to remember that ultrasound works better in samples that crystallize slowly, and works also better when ultrasound is applied at the onset of crystallization. What about agitation? So as I said before, when we do these crystallizations, we place our melted sample in a crystallization cell. And what we do is, as soon as we place that hot sample in our cell, we start agitation with a magnetic stirrer. I mean, this is a small, we usually do this in a very small scale, about 100 grams. So with a magnetic stirrer, using either 100 and 200 RPM, what we try to do is to induce a heat transfer from the water, from the jacket of the cell that is circulating water to the sample so that we induce a very fast cooling, or as fast as we can. But what we do is when the sample reaches that crystallization temperature that we're targeting, we stop the agitation. And we stop the agitation, and then we either apply ultrasound right away, which would be the case of applying ultrasound without any crystals, or we apply ultrasound when we see the first turbidity appearing in the system. That would be the case of the applying ultrasound at the onset of crystallization. So we always wondered what happened if, instead of stopping the agitation at 10 minutes, what happened if we continue the agitation throughout the entire crystallization process. And these are some results. This is data collected by Jetta Kadamne back in 2018. And she was a PhD student in my lab. And we did this specifically for two temperatures. We did one temperature in the middle, but I'm going to show only these two. And we can see, so the blue data are the samples crystallized without ultrasound. The red data are the samples crystallized with ultrasound. Within the blue, the lighter data, for example, here is the one where we continue the agitation throughout the entire crystallization process, and the other one is where we stop the agitation in 10 minutes and we let the sample crystallize under static conditions. The red one, same thing, both with ultrasound. The light red or pink is a sample where we continue agitation, and the red one is the one where we stop the agitation. Now we can see that ultrasound, in this case, a low temperature, affected the crystallization kinetics no matter what, whether we stop the agitation or whether we continue the agitation process. Now, when we crystallize a sample at a higher temperature, the first thing that we see that, of course, if we continue the agitation, crystallization occurs faster. And that's something that many people have proven before, that agitation induces crystallization. Now, when we apply ultrasound, we see that indeed, if we continue the agitation, you see this line here with a light pink, the induction of crystallization is not as important as if we apply ultrasound and then we let the sample crystallize statically. And this induction in the crystallization are also seen in changes in viscosity of the systems, with higher viscosities obtained for the samples that were crystallized with ultrasound and without agitation. So the bottom line is that yes, we can leave the agitation on, but really it's better if we crystallize these samples without agitation to avoid bubble dissolution. That's what we think is happening. When you apply ultrasound, you have all these bubbles are being formed, and if you continue with agitation, the bubbles are going to dissolve a lot faster. So yes, sonication works better under static conditions. So as I said before, one of the biggest challenges that we had was the fact that every time we changed a fat system, we had to start all over again. I mean, we knew more or less where to go, what to change, how to go about it, but it was very frustrating to see that a condition that worked for one system will not necessarily work for another system. So we decided to do a study. This was a study in collaboration with Dr. Aiko from University of Georgia, where he designed interstratified samples with 20 and 30% content of saturated fatty acids. And within those samples, 20% of saturated fatty acids were driven by what were really palmitic and or stearic, right? So basically trying to compare not only the content of saturation, but also the type of fatty acids that is driving that, that saturated level. So the first thing that we found is that when we used stearic acid, 20% ultrasound did affect the crystallization kinetics of the sample, but only at high temperatures or lower supercoolings. Now, you would think that if you have very similar supercooling or very similar driving force, you will have the same effect on a palmitic-based interstratified sample. So, but the result was that no, we did not see an effect of sonication in the palm-based samples. So again, palm-based samples with 20% of saturated fatty acids, there's no effect of ultrasound, even though the supercooling was the same to the one that we used in the stearic sample, and the driving force was very similar. So really, sonication did not affect the crystallization of palmitic acid-based samples. Now, when we increased the level of saturation to 30%, now ultrasound started working for the C16 samples, and we see an induction in the crystallization, especially at higher temperatures, and of course, even a greater effect for the stearic acid. And now we see an effect for stearic acid at even higher supercooling, right? So as a take-home message, sonication works better in stearic-based sample. I'm going to show you some data in a little bit that also supports this conclusion. And but also it has limited effect when the level of saturation goes too low. So when we decrease the level of saturation to about 20%, the effect of ultrasound is not as good as we would expect. So over the years, we've seen a lot of papers on ultrasound, and most of them use frequencies of 20 kilohertz, but some of them have used slightly higher frequencies. Some of the studies have used, for example, one of these ultrasonic water baths, and these baths use frequencies a little bit higher, between 40 and 65 kilohertz. So we decided to design an experiment where we would compare the use of ultrasound at 20 kilohertz versus 40 kilohertz. And we compared this work by Roberta Claro da Silva back in 2018. She was a postdoc in my lab. So what we did is we applied different power levels. So you see these are the amplitude of vibration of the tip. Remember that I said before that amplitude of vibration is related to the power of the ultrasound. So we tested a low power level and a high power level. And for the high power level, we tested different durations, 5, 10, and 15 seconds. So we look at this figure of solid fat content versus time. We see that this is a very, very slow crystallization of this sample. I mean, this sample was turbid with definitely crystals, but the NMR will not peak any solid fat content in here. And the best results were found with the low power level, with a 24 microns for 10 seconds, and with the higher power level also for 10 seconds, right? So these 10 seconds seem to be the sweet spot in here. Now, when we applied ultrasound at that same high power level for a shorter duration, then we see a little bit of a less effect of ultrasound. And when we apply ultrasound for a longer time, the effect of ultrasound is even worse. So even though ultrasound worked for all these conditions, really it depended quite a bit on the power level and on the duration. Now, when we applied ultrasound at 40 kilohertz, these were very interesting results, because now the lower power level for 10 seconds was not effective, not very effective. And the one that worked the best was the higher power level for 15 seconds. So the one that didn't work for 20 kilohertz worked really well for 40 kilohertz. And these changes in crystallization kinetics were also shown on the elasticity of the sample, where samples crystallized with 20 kilohertz were a lot had a higher elasticity compared to the ones at 40 kilohertz. So why do we think this is happening? Well, it kind of these results kind of make sense because really what we know from studies in ecosystems is that cavitation thresholds increase as we increase the frequency. What does that mean? That means that we need higher power levels to create cavitation as the frequency goes up. So, I mean, that's what it's seen here, right? We need at least 108 microns to induce the crystallization in this system, and a longer duration to make sure that the sample crystallizes, or we use the crystallization in this sample. And this makes sense that this is why, for example, when you use diagnostic ultrasound for medical purposes, you use very high frequency. One of the reasons why we use very high frequency, so that we don't create cavities in the human body. We definitely don't want to do that. So most of the studies that we've done so far, we've done it in a crystallization cell, in batch. So we decided the next step would be to use a flow cell. This is work by Yu-Bin Yi. He was a PhD student in my lab. And what we did is we let the sample go through the flow cell. We collected the first sample as a control, and then we collected sample every minute in different tubes. And we stored those tubes for 60 minutes at 35 degrees Celsius. So when we applied ultrasound at 75 watts, that's a lower power level, we saw that the solid fat content increased. We induced the crystallization in these samples. And no matter how we applied ultrasound in a continuous or in pulses, the increase in solid fat content was observed. Now, when we increased the power level, what we saw is that, yes, we did increase the crystallization kinetics for the first few tubes, but as the sample was coming out of the flow cell, it kind of melted the crystals. We had fewer crystals in the continuous mode. But this could be reverted by using pulses. You see, when we use the 5, 10, and 15-second pulses, we still see an reduction in the crystallization. Not as good as the one that we saw at lower power levels here. And if the power level is even higher, we even see a greater reduction of the solid fat content in these samples that can be again reverted by using pulses. So what this is telling us, our hypothesis is that if we apply ultrasound for very high power levels, what happens is we're going to generate a temperature increase, an increase in temperature in the sample, and that increase in temperature is going to melt our crystals and is going to actually give us the opposite effect of what we want in ultrasound, which is to melt the crystals and create something that is softer. But if that is the case, that we have to use a high power level for some reason, then we can use pulses to help dissipate that increase in temperature. So I'd like to talk a little bit about what happens during storage. This is very recent research that was performed by Joo-Hee Lee. She's a PhD student in my lab. She's graduating this semester. And what she did is she crystallized an all-purpose shortening. This is a pump-based shortening with about 40% of saturated fatty acids. And she stored the samples for 6 months because, one of the questions we had from people is, okay, you crystallize your sample, you evaluate your properties, maybe after 48 hours. But what happens if you store your sample over time? Do you still see these changes in physical properties? I'm going to show just briefly here elasticity and hardness, but we have a lot more data on this. So if you have questions, just let me know. But as we see here that we did have a higher elasticity on the sample that has been crystallized after 60 minutes, and we see that increase at 48 hours as well. But to me, the most important result from here is that if you look at this gray bar, which is the sonicated sample, that level, level of G prime, that value of G prime doesn't change during the storage, right? So we're able to reach the final structure of the material right after the 60 minutes of crystallization. While if we look at the black bars, which are the samples that are not sonicated, the G prime values are lower and they keep increasing during storage. So it takes about 12 weeks for this sample to reach the same structure that we will reach with ultrasound at 60 minutes. That's, to me, for a fat that crystallizes so slowly like palm oil, this is a very significant and important result that can help producers achieve a higher quality product. And the very similar result was observed for 5 degrees Celsius. And again, very similar with hardness, we see the same trends. Our sonicated samples are harder than non-sonicated ones. And in this case, at 25, the hardness keeps increasing. And at 5 degrees Celsius, they reach a plateau very fast. But really, that final hardness is almost reached at 48 hours for the sonicated sample. So what happens if we want to scale up? Most of these studies were performed in batch. So back about 3 years ago, we received a grant from the state of Utah to scale up our technology in a scraped surface heat exchanger. So we bought one benchtop scraped surface heat exchanger. And this is the work from Thais Silva. She was a postdoc in my lab. She did a great job. She collected a lot of data. So here I'm going to show just a few of these data. Again, if you have more questions, just let me know. I'll be happy to forward you to the papers and to answer as much as I can. So in a scraped surface heat exchanger, as many of you know, we have 2 barrels. The 2 barrels have temperature control. In the first barrel, we basically induce the first crystals, the nucleation of the sample. The second barrel, we continue that nucleation and crystal growth. And then the sample goes through a pin worker where the sample is agitated and those crystals are broken down a little bit, and it helps with the texture of the sample. So after going through these 2 barrels and the pin worker, the sample is collected and used or stored for further use. So in our case, the first study that we did, we used an interesterified soybean oil with a melting point of about 42 degrees Celsius, solid fat, and a content of saturated fatty acids of 32%. And we used a crystallization temperature of 32 degrees Celsius. So what we did is we placed the ultrasound at the end of the system. And because we didn't know this is the first time that we did this, we tested different power levels. We tested continuous application and also 5 and 10 second pulses. We collected the samples and we measured the physical properties. So the first thing that is important to note here, if we look at this picture, what the samples look like, the control was pretty liquidy. The sample sonicated with 50% intensity or power with 5 second pulse was a lot harder, just visually. But interestingly here, the ones that we sonicated with 70% and 80% power were a lot softer, right? So really higher power level, like we said before, not always means better effect of ultrasound. And when we measure the elasticity, we see a higher elasticity here with a 50% using the 5 second pulses. Same thing with the hardness and same thing with the oil binding capacity. However, we saw also quite promising results with a 20% sample and in both hardness and oil binding capacity. So the next step was to say, okay, we know that the 20% and the 50% are really good conditions when ultrasound is placed after the pin worker. But what happens when we place ultrasound, maybe in other places, maybe before the first barrel or between the first barrel and the second barrel, or between the second barrel and the pin worker. So we did that. And what we found, you can see here the pictures, is that really ultrasound worked better when it was placed towards the end of the system, either in this position here between the second barrel and the pin worker or at the end. And that is translated also in any increases in hardness, increases in G primes, and increases in oil binding capacity. So really the theory behind this is that really at this point, we have enough crystal, these conditions will represent that onset of crystallization where we want ultrasound to work. So because we studied this in a soybean-based sample, we decided to try to find similar results with palm-based. So we started by testing a 50% power level for 10 seconds at the end of the system. And what we found is that actually when we crystallize at 32 degrees Celsius, which would be a reasonable crystallization temperature based on the results that we found for the soybean oil, we didn't see any effect of ultrasound. And actually we saw that the ultrasound melted the sample quite a bit. But we did see that the ultrasound worked quite well at lower temperatures, as shown by hardness here and G prime and oil binding capacity. Again, note here how the oil binding capacity, G prime, and also hardness decreases with ultrasound at higher temperatures. So pretty surprising results that we were not expecting. And this also corroborates our previous hypothesis that ultrasound works not as well in palm-based samples. We need a lot more energy to induce crystallization in a palm-based sample. We then repeated the experiments by placing ultrasound in different spots, different places of this scraped surface heat exchanger, and we found very similar results to what we found with the soybean samples, where this position here between the second barrel and the pin worker or after the pin worker were more effective at inducing crystallization. So figuring out where to place that ultrasound, depending on the type of sample and the crystallization kinetics that you have in your sample, is going to be very important to make sure that ultrasound is giving results that you expect. So overall, what are the conditions that work better with ultrasound that you have to look for? First of all, we do know that ultrasound works better when it's applied at the onset of crystallization, either when you're applying ultrasound in bulk or in a scraped surface heat exchanger. We know that it works better in samples that are crystallized under isothermal conditions and static conditions. And we also know that it works better at intermediate or even high crystallization temperatures. If we work at too high crystallization temperatures, you might want to play around with the power level and the duration of the ultrasound signal. These intermediate and high temperatures are usually selected to create a low supercooling and a slow crystallization rate. Perhaps the best application of ultrasound is for fats that have low level of saturated fatty acids, again, to create that structure that is lost in these fats because they have low level of SATs. And again, we can work with short pulses or intermediate power if needed. Again, also keeping in mind to avoid oxidation, avoid heating, and avoid melting of the sample. High power levels are not always better. In some cases, too high power levels can melt our samples, so we have to keep an eye on that. And stearic-based samples seem to work better than palmitic, or at least if you're using palmitic, you might need more drastic sonication conditions or lower crystallization temperatures. And last but not least, it's important to know that the effects that you see due to sonication are maintained during storage, at least for 6 months, and that's what we tested. With that, I would like to thank everybody that was involved in this research, from undergrad students that actually started this type of research. This research was started by undergrad visiting scholar from Brazil, grad students, visiting scholars, postdocs. Everybody that has gone through my lab has made tremendous contribution to this research. I'd like to thank all the agencies that provided financial support and also discussions of the results and interest in this technology that helped us figure out how things work and what things were important for the industry. And I would like to finish up thanking AOCS for allowing me to present my research every year, year after year in the annual meeting, and to my colleagues that provided so many good questions and insights and pushed us beyond the limits to get better things going. And last but not least, I'd like to thank the Journal of the American Oil Chemist Society for allowing us publish our papers in the journal. The editorial board, the reviewers, they always been very, very helpful in the comments that they provided, with the ultimate goal always to improve the quality of our research. With that, I would like to thank you for being here, and I will be more than happy to answer any questions. Thank you.
Silvana, at this point, we'll start the question and answer session. I don't know if anybody has any time constraints, but we're going to stay on until all the questions are answered. And thank you for those of you who have entered questions into the Google Doc, and I will basically go through that, through those questions, the ones that were submitted from the audience. And so I'm just going to start by asking the first one and working through the list. First contributed question is, are there any examples of industrial use of sonication?
Not that I know so far. We would like to see, we had some interest from companies, and we would like to see more research going on. And I think that research that we've done with the scraped surface heat exchanger is a start, and it's a starting point to make it more available for the industry.
Is it used for other materials besides lipids? Commercially, I mean.
As far as I know, it's used a lot in the drug industry, ultrasound. Probably not in a scraped surface heat exchanger, probably in batch. I'm not very familiar how they do synthesis of drugs, but I believe that ultrasound is used a lot for drug synthesis and crystallization.
Yeah, that's my understanding as well.
Mm-hmm.
Here's a question about the melting point of this. So is the melting point of the sample the optimal temperature to apply sonication, or do you desire the formation of more crystals before applying sonication? I think you answered this, but why don't you mention it again?
Yeah, so we want to be slightly below the melting point, right? We don't want to be right at the melting point. We want to be usually between 2 or 3 degrees Celsius below the melting point of the sample. That's what we found that works the best. And we want to apply ultrasound just at the beginning of the crystallization. Sometimes we measure the solid fat content, just before sonicating, and it's always 0, right? And you see how, how NMR doesn't pick up a lot of crystals, right? So you can have, you can see crystals in your sample, and NMR still gives you a 0, right? It has an error of about 1%. So we do want to apply ultrasound at the very, very first onset of crystallization. We became very, very good at seeing the first turbidity coming up, and then that's when we apply ultrasound.
So a question that sort of goes hand in hand with that is about temperature control. And does the high temperature during cavitation cause any damage?
Yes, it does. If you don't control the temperature, your temperature during sonication will go up. So we work with small amount of samples, and we keep the temperature with an external water bath that circulates through our cell. And while doing that and applying ultrasound only for 10 seconds, we always have to remember that we only apply ultrasound for 10 seconds. We see maybe a 1.5 degrees Celsius of increase in temperature. If you don't cool it while you're applied ultrasound, you will see up to 10 to 20 degrees Celsius of increase in temperature. So controlling temperatures during sonication is very, very important.
Yeah. Does it cause any chemical changes in the product, in particular oxidation?
Thank you for that question. We always get that question. It doesn't. We did measure the triacylglycerol composition of the fats before and after crystallization, before and after sonication. And we've done a very extensive study on oxidation. Juhi Lee, my student that is graduating this semester, she measured degree of oxidation in samples that have been sonicated at different conditions, and we also measure volatiles. So under the conditions that we use for crystallization of fats, we did not see any effect on peroxide values, OSIs, or volatile compounds. So we are very, very confident that sonication is not inducing oxidation. And again, I wanted to emphasize, we only apply ultrasound for 10 seconds. If you apply ultrasound for a minute, 5 minutes, everything changes.
Right, but one can understand that the high pressures and temperatures at the point of the bubble collapse could cause some changes, but apparently not lipid oxidation over that shorter time.
Yeah.
Okay, great.
Cool.
This question relates to oleogels, I think. So can sonication reduce the percentage of gelator added and have similar results?
It does. Actually, we have a few papers on that. Annabella Giacomosi, she was a visiting scholar in my lab a few years ago under a Fulbright scholarship. And she published 2 papers on that area. And I'm going to talk a little bit about that in the presentation that I'm giving in the annual meeting on May 4th. So if you're interested and if you're going to the annual meeting, just don't miss that presentation. If you're not, I can always send you the citation of the papers so that you can read it. But yes, we had to tweak a little bit the processing conditions for the oleogels, because oleogels, as you probably know, crystallize very, very fast. So an ultrasound doesn't work that well for samples that crystallize fast. But we were able to reduce the amount to obtain the same physical properties of samples with lower amount of oleogel.
Perfect. Next question is about structural analysis, and have you carried any out? And I'm not quite sure what structural analysis is being questioned here, but I'll leave it to you for free rein.
Structural analysis, the structural analysis that we do is really microscopy, polarized light microscopy. We measure G prime that will give you an idea of the molecular strength, the strength between molecular organization of your crystalline network. We haven't done any, well, we did some polymorphism analysis in the samples that were relevant, but we never did any SACs or ultra SACs. I would love to, ultra small angle X-ray. I would really like to do that in the future. Yes.
Yeah, sounds great. This is an interesting question about gas. And if you dissolved different gases into the oil, would you get different results?
You actually, that's my next USDA submission. So for those that are, looking for ideas for USDA, actually, that's what we're going to evaluate to see how the effect of gas dissolved, how does the type of gas affect the efficiency of ultrasound? Yes, very good question. Thank you.
Can you predict what you might find?
I think it's going to depend. So one of the hypotheses that we have is that the efficiency of ultrasound or the effect of ultrasound is dependent on the viscosity and other physical properties of the oil that you are sonicating. So I think it depends on how these gases affect the physical properties of the oil in terms of density, viscosity, interfacial properties. And so that's what our next proposal is going to do. So if USDA gives us the money, maybe next year I'll give a presentation in the next annual meeting.
So I assume that the solubility of the gas would have an effect.
Yeah, solubility and yeah, definitely.
Okay. Does ultrasound work on emulsions, particularly low-fat emulsions like 30 to 40%?
So I'm going to talk a little bit about these two next in a couple of weeks in the annual meeting. I'm going to show some results from Thais da Silva. She came to my lab from Brazil for a 6 months internship while she was doing her PhD in Brazil. And she tested ultrasound in oleogels, but also in emulsion gels. And she made, I believe, emulsion gels with 25% water. So they were water in oil emulsions. And she did find a greater stability in the sonicated samples compared to the non-sonicated ones. So that's the only system where we tested ultrasound in emulsions. It would be interesting to explore that further, yes.
Next question is about differences between a cocoa butter type fat versus an interstratified fat. I'm not sure you haven't already addressed that, but if you would say something more about it.
Yeah, so, most of the research that we've done was based on fats with low level of saturated fatty acids. And that's because I'm particularly interested in finding or developing structure in samples that have low level of SATs. And that's the main limitation of these samples. They are healthy for you, they're better for you, but if we don't have that structure, we can't use it. So most of our research was done in samples like the intraesterified soybean oil. We did a few tests with confectionery fats, like a palm kernel based one. And that study was mainly based on oil migration. And we did find that ultrasound improved the oil migration, decreased the oil migration, improved the oil binding capacity. And so that's mainly what I did. We didn't do much with cocoa butter. We had some research that's not published on blends of cocoa butter equivalents and cocoa butter, and we applied ultrasound to when we were able to, for example, eliminate a eutectic point between those mixtures, specific mixtures of these two components. But that's not published yet, so I can't talk too much. I can't remember exactly the results, but it has some promise.
So next question is, why does palmitic acid behave differently from stearic acid?
$1,000,000 question. I wish I knew. I don't know. I don't know why, because usually we design the experiments to have the same supercooling, the same or very similar supercooling, very similar content of saturated fatty acids, very similar driving force. So you would think that the crystallization kinetics will be the same or similar, and ultrasound will work similarly. One hypothesis that I can think of is probably viscosity, and probably we should do a little bit more systematic approach measuring. I think the secret will be to the future research in ultrasound will be to evaluate the physical properties of those materials and how that affects the efficiency of ultrasound. Because, yeah, so I think that's what I would like to do next. Because, for example, if you were to apply ultrasound in chocolate, right? That's a question that I always get. Can you use ultrasound in chocolate to avoid tempering, right? I think chocolate is too viscous. So if your sample is too viscous, you have a hard time generating these bubbles and generating these high shear forces. You will need a lot more power to obtain a similar result. So if your sample is too viscous, I think ultrasound might not be very efficient.
Does it have anything to do with minor impurities?
It could be too. Yeah, minor components could be. Yeah. Good point.
Last question. Are 10 seconds recommended with 2 pulses of 5 seconds? So it's not quite a question, but I think the question is 1 pulse of 10 seconds or 2 pulses of 5 seconds?
It depends on the fat, really. Most of the time, we applied only 10 seconds continuously. But for example, in the oleo gel, we ended up using pulses. And I think it depends on your fat and on the crystallization behavior of the fat. It's going to depend. You'll have to optimize it.
And that brings us to the end of the questions that were posted on the Google Doc. And so that brings us to the end of the question and answer period. And so again, thank you very much for the presentation and congratulations.